Hi, I'm Alexander McCrae, and I'm going to be covering the MobilityFirst MSocket Library. What is the MSocket Library? It's a user-space Java library providing a socket API. It utilizes the MobilityFirst internet architecture, and it basically allows for peers to move IP addresses or have multiple IP addresses and keep some of the same guarantees that TCP gives us. It actually wraps around TCP sockets, as we'll see. So what problem is this addressing? Well, it's addressing that IP addresses are being conflated with identity. This isn't intentional. IP addresses are meant to be network addresses. But over time, since we didn't really have a solution for this, we've used them as IDs. More and more mobile phones are being used, and those are often requiring mobility. If we ever wanted peer-to-peer mobile phones, we would like mobile phones talking to each other, we'd need a way for them to address each other. MobilityFirst provides that sort of architecture and that infrastructure to do so. Current solutions to this problem either only handle a subset of the situations or require a massive amount of changes to internet architectures. So what are the mobility situations? What happens at connection time? So what happens if a peer moves while being connected to or while connecting to another peer? Individual. So if there is already a connection established and one peer chooses to move IP addresses or moves IP addresses, how is that handled? Do they have to reestablish a new TCP connection, or can they migrate their old TCP connection or some other connection? And then simultaneous. What happens if both of them move at the same time or are constantly moving? There's a couple solutions to this that we'll get into. What characteristics should a solution have? Well, the solution should solve all of these mobility situations. It shouldn't require massive changes to current internet technologies. It should be able to handle tomorrow's scale of the internet, and it should maintain the end-to-end principle if possible. And we should have a general solution, something like DNS, rather than specific ones, as we already have specific ones that you've probably used without even noticing, and they work well in the environments that they're in. So let's look at some previous work to sort of see why, compare MSocket to it. The end-to-end approach to host mobility was a paper by a couple people at MIT in the 2000s. It was presented at MobiConf. It uses DNS to update the IP address of the domain name, and it includes a token in an optional TCP header that identifies the connection. So if you were to ever move IP addresses, you would just update your domain name, and then you could your other peer would go requery the DNS server and pull it back down and connect to your new IP address. It allows migration of TCP streams by using this TCP header and that token in the header. So it changes some of the semantics or the state machine of TCP, but that isn't the end of the world, as it is completely compatible with normal TCP, and that's really important. It handles most mobility situations, including both peers moving, so all mobility situations, but it means every mobile peer actually has to have a domain name. And there's a couple reasons that isn't feasible, especially with mobile phones. It also has the issue of DNS propagation. Takes a little bit. Mobile IP. This is probably the most common one today. It uses a proxy back to your router. So if you are a mobile phone behind a router, and then you change an IP address, so you get off of that network and move to another network, your phone is actually going to send your packets back to your home network and then out to your destination. And that keeps it so that your other peer, or whoever you're sending the end destination to, doesn't actually ever see you change IP addresses, because it's just using your router's IP address. This is nice because it's compatible with existing technology. It handles all forms of peer mobility. So if both peers are moving, they can just both use their home router addresses and just route back, and neither of them will know. but you don't really have a way of addressing these peers in the first place. This requires large changes into the internet architecture, but a lot of those have already been done, as this is coming to mobile phones quite soon, or already has in some cases. And it does break the end-to-end principle. Quick, this is a new protocol. Each logical connection is given a connection ID. And then whenever a peer migrates, it'll go and connect back to that server or whoever it is connecting to, and it'll probe a path. So this isn't actually sending the data yet, but it's just making sure it can connect. Once a peer has migrated and basically it probed and said, yes, I can get there, it will start sending data and wait for an authentication challenge. The other peer will then send the authentication challenge and then start communicating back and forth on that logical connection. Really nice is that the Quick protocol has defined its security really well. It handles most mobility situations, but you still need a third party or something to allow for simultaneous mobility. So if both peers move at the same time, they don't know exactly how to get back to each other. And it's compatible with existing technology. This is already on UDP, right? So it's another layer on top, and it's being used more and more in Google Chrome and with HTTP, it's going to be used quite a bit. One of the big weaknesses is that simultaneous mobility is not handled. Should be noted that for most applications, they probably don't need simultaneous mobility. So like how we use the web today doesn't really necessarily need it. So now let's get into MobilityFirst, particularly the MSocket. So MobilityFirst started out in 2010 as part of the National Science Foundation's Future Internet Architecture Program. We've covered this in class. The idea was to basically take a clean slate on how we change the internet and how we design the internet. And then each project was to create a prototype as a realization of this new internet. Some notable projects alongside it were named data networking, Nebula, Expressive, and ChoiceNet. Components of MobilityFirst that MSocket uses are the separation of name and addressing. So what happens is, instead of using IP addresses as an identification, we use GUIDs. And a GUID is basically just an integer that is unique to that user. The GNS, so Global Name Service, you can think of it as DNS. It's basically mapping GUIDs back to IP addresses, but the difference between DNS is that it allows you to update it rather quickly, like extremely quickly. And so it could actually be built into DNS. So DNS would map down to GUID, and then GUID would map down to IP address. And what you'd have is your IP addresses changing under the GUID. So the GUID might map to one or more IP addresses if it's multi-homed or not. Lastly, they'll use self-certifying public-private key authentication. I'm not going to go very far into this, but this is just basically, it allows you to authenticate the peer as the original peer and confirm that it is the original peer. So we can sort of visualize these components here. So peer B might go up to the DNS server to map a domain name down to an IP address or a GUID, and then that will go to the GNS server to map it down to an IP address so it can connect to peer A. We'll see how these play into the mobility situations with the MSocket library. So this is the interface. It's sort of similar to the BSD interface. You can see that up here we create a new MSocket, and then we get the inputs and output streams. It's a little more Java-y than you might expect. And it basically works how the BSD sockets may work. Okay, so we're going to get into how it works under the hood now. So at a high level, it's identified by a client ID and a server ID. So these are the GUIDs that were mentioned before. Under it, there is one or more TCP sockets. And this is really important. There can be multiple TCP sockets, all with different IP addresses if you're multi-homed, i.e. your your computer is actually connected to multiple networks and has multiple IP addresses. We're going to call these TCP sockets that are underlying TCP sockets as flow paths, and they are identified by normal TCP identifiers. There is a new packet format that sits on top of the TCP packet, and this includes things like a separate sequence number, a cumulative acknowledgement, and it really needs these things because it is merging multiple TCP streams into one stream. So those sequence numbers that are on those TCP streams aren't user viewable in the first place. And you can't really migrate multiple TCP streams using those sequence numbers. So we use a higher level packet to allow us to reorder in the buffers. And that's another thing we have is user space input and output buffers so that we can do that ordering. It's also important to have this new packet format for migrating because we're not going to be using the same TCP sockets as we'll see soon. Yeah, so this is just a overview of the MSocket packet. It's TCP independent sequence numbers, cumulative ACK, and then we'll get into the details of it. So connection establishment. The client will connect to the server using a TCP socket in the first place. It's really important to note that both peers must be using the MSocket library. This is not compatible with normal TCP because of that new packet format. And so these two TCP sockets will establish themselves as one flow path between the two peers, and it'll establish a connection ID, a path ID, and then a connectionless control socket address. These are important for migrating, and we'll get into it a little more later. If a peer moves during the connection establishment, basically you just requery the GNS server and get that new IP address and then retry. For data transfer, it's basically just using that high-level packet that we talked about before. Because it includes that sequence number, cumulative ACK, and length of payload that wasn't normally or is separate from TCP sockets, you can actually send them over multiple TCP sockets, sort of guaranteeing that it will get there somehow as long as the peers have at least one flow path, which is a TCP socket under the MSocket library between them, and that it's working. Any duplicate packets don't have the same semantics that TCP does with duplicate packets. Instead, or duplicate ACKs, instead it'll just ignore them. So what happens now when we have one peer move an IP address? Well, if it's the server moving, so the one who was listening, it will actually send over that control socket that I had mentioned before. It'll send a reconnect address, and so that's a control message, and it will tell the client where to reconnect to. Okay, so this assumes that the server actually knows where to reconnect to, or the server has already migrated and is now telling it to connect to this new address, and then an authentication will happen to ensure that this peer is actually the peer. All of the underlying TCP connections between them will be migrated over. So they close, they open a new TCP connection, and then they'll basically send some more control signals to make sure that they know who each other are, and then tell each other what missing data they have, or what has not been acknowledged net from their own output buffers. A complete high-level connection is migrated when at least one flow path is reestablished. So as long as there's one path between the two peers, it's considered migrated. And each flow path can be migrated independently. So you may only be changing one of your multi-homed IP addresses. And so this allows you to not have all your flow paths change at once. So you don't have to reestablish all your connections. If both move at the same time, there's no way for them to connect, right? Because they're sending to the wrong IP addresses. And so what they'll do is they'll query the GNS, see if anything's changed. And if they have, they'll try to reconnect to each other that way. So basically just sending the reconnects control messages. So this is pretty good. I mean, it has a lot of strengths to it. It handles all forms of mobility. Although I didn't cover it, it does handle it handles NAT by using a proxy. And only peers who are using this have to change their socket library. So you don't get to use normal CBSD socket library. But if this is more of an application specific thing, which is one of its weaknesses, it's also not suitable for TCP or non-TCP like connections. So this couldn't be used for UDP, and still has some of the issues like headline blocking that we've seen resolved in Quick. It also fails to stay compatible with normal TCP, so it's going to require both peers to have the MSocket library up. In conclusion, the architecture and components set out by the MobilityFirst group are fantastic. I mean, this has really paved the way for us to add mobility to the internet. This realization of the stack isn't perfect, but it is good enough to play around with it, and I've included the GitHub link and the technical report, which I'm basing this presentation off, to the side. Thank you.